Sorry, video. Enable start. This one only. Huh? This is the video which is shown. I know, but this is also on. Because when I am speaking, this only will be popped up. Anyway, I am already unmuted. Allow me to turn on the video, please. Which one? I know, if you look at yes, thank you. You can't start your video because the host has stopped. Yes. Okay. Okay, then. So I think probably we'll start again. Yeah. So what we will do now, actually, whatever we have covered right now, it's all very basic linear algebra. We'll try to do the same thing in the Sage Math, and we'll come back and then we'll switch over. Will that fine? Yeah. So we'll do something whatever we are trying to do right now in the Sage Math. So we have already introduced, first of all, how do we have to create a vector, and then how to do a simple addition, scalar multiplication, finding norms, etc. Correct? So let's do some more things. So let's try to do linear combination. Okay. So I can set the V whatever we want. I already told you that whenever you need a vector space, then you can either create it like using a span, or you can create it right away using your predefined vector spaces already there. So if I have vector space RR, then anybody actually now you are creating it is just a real number. That's all. So what I wanted was actually, let's say R power 4, meaning R4. That means now I have a vector space R4 in me, in my hand. Okay. We'll do some more computations, but first we will create some vectors. So let's create a vector, and that vector first be a real number, real vector, and maybe 1, 1, 2, -1. Some special numbers we picked up. So V2 is another vector. That's also a real number, real vector. So 2, 3, 5, -4. Okay, fine. Let's create one more vector, V3. That's also a real vector. And 3, 4, 7, -5. Okay. So these are my vectors. I removed some portions so that we'll have some more. So if I simply print V, then what does it say? It says a vector space of dimension 4 over real field with 53 bits of precision. 53 bits of precision is, I think, 17 decimal places. I'm not sure exactly. Vinay, can you confirm that? How much is the 53 bits of precision on decimal numbers? I forgot. I think it's 17 decimal places. Let's see. And if I suppose change it to QQ, we have already discussed that this is a vector space of dimension 4 over a rational field. Yeah, fine. 16 decimal places. Yes, it's 16 decimal places. Now, what we want to do, we wanted a span. How do we actually generate a span? You know already that you are taking a vector from somewhere and you are trying to create a span, and that span must be a subspace of V, correct? That's what we were discussing. So the way we create a span is using capital V dot span and then throw some vectors which are being defined on those vector space. For example, I'm passing a list, and let's say I give V1 and let's say I give V1. So that means what we are doing right now here is we are actually, this is what? This is a, I just mentioned in the theory. This is a line in line of V, right? Just a line of V, meaning a line passing through origin. If I compile this, now it gives me a basis for that particular vector space. Obviously, what is happening here? I have a vector 1, 1, 2, minus 1, and that becomes a basis for me because everything else on that line becomes a scalar multiple of that. Yeah. And you can notice that they are real numbers as it is. Yeah. If I change my vector space to QQ, now you see the basis has been simply 1, 1, 2, minus 4, minus 1 rather than that. Is the zoom is all right? Everybody is okay with that? Yeah. Are you checking the chat? Yeah. Okay, fine, good. Let me circle back to R. So now I can try checking whether V2 is in the span or not. So maybe what will I do? I will call this as a W1. What did I do? I just actually create a W1 and equal to. That means anything which has been returned from the right-hand side function will be stored in W1. That's what it says. So now I can say who's my W1 just like that. And it tells me what it was already telling me. Okay. So now I can do one thing. I can write whether V2 is in the W or not. I think it is V2 in W1. Yeah, that's it. So if I say V2 in W1, it says true or false. That will simply say that whether V2 is actually contained in W1 or not. Remember, this is definitely not possible when you are trying to do it in Python. But here the implementation is entirely different. You know what does that mean? That means what? Are we really checking whether V2 is in W1 or not? We are not actually checking that. What we are really checking here is whether V2 is a linear combination of V1 or not. That's all we are checking. Yeah, that's so powerful than to check everything else. For example, with irrational entities, like squares of bios. But irrational is not a field, right? Set of all irrationals. So what we can do is, ah, okay. Okay, that is, okay, that's possible by just writing it square root of 2. Maybe if you print V3, then that has been converted back into a real number like that. So if you keep it as a real field, meaning rational field itself, then oh, I'm sorry, I have to keep it here. RR. I doubt whether irrational numbers is possible to have it like that as long as it's as a separate number, right? Whether it's singular, no. That's what, if you keep it double R, then automatically what will happen is actually it will convert into a real numbers up to some precision. Yes. It's the same 53 bits of precision. Until that, it will convert. So it's just the square root of 2 is 1.414213562A3, such things. So square root of 2 is never been treated as square root of 3 now. Yeah, I don't think so. There's a way of doing it. Did you find any way? Yes. Yeah. So we can't do it. Because I wanted to deal with vector space. That means the number which I'm picking up from supposed to be inside a vector space. So if you need a really a irrational number to be dealt with, then I don't think so. If you just simply remove RR. Yes. That's again just a real number, sorry, rational number. It just treats it as a symbolic calculation, right? Yes, that's all it will do. Yeah. Yeah. Anyway, I don't usually suggest to do it as it is like that, because it might be first of all slower. Yeah, it will be first of all slower, and second thing is there are some discrepancies when it comes to checking whether it is the particular vector is in the span or whether it's a linear combination of something else like that. It might result in false where you would be theoretically expecting true. So that problems may occur. Okay. Yeah. So that problem is there. Okay, let me put back everything to RR now. So now I identified actually now whether V2 is in W1 or not. Obviously, I can do V1 is in W1 or not. Yes. That means 2 times V1 also should be in W1. That means any alpha times I have, that should be in W1, correct? That means I think square root of 20 into V1 should also be in W1, but it is saying no. Why? This is sometimes this is a problem when you do this. Because this number has never been considered as a real number now. Huh? RR power 4, no? Yes. Yeah, one way of checking it is just take the W1 style. Yeah, it's never a. No. Yeah, I will check that and get back to you. Okay, just I don't think so. Previous? I don't. Still false. Let's check whether. Yeah, see, this works. That means actually it is still considered as a number in a irrational number, and then multiplying it is becoming actually a element in irrational field, and it is trying to check it in W1, and that's saying it's false. So there should be a way actually, we should tell that the square root of 4 is a real number. So that is possible. I think in a minute, when I will check and let me know. Yes, sir. dot n of you're saying. Yeah, that's. Yeah, I did. No, I understand. What's the problem is the square root of 4 should be considered as a first of all a real number, because W1 is not a vector space over QQ. The W1 is actually a vector space over RR, right? Meaning the real number field. So it should be a real number. So as Sarah suggested, one way of doing it is actually look at the corresponding numerical approximation of that square root of 4 and then multiply with V1, and that result is true. That's correct. Yeah. So all that I'm trying to say was, you be very careful, first of all, when you are actually dealing with these kind of numbers into Sage Math, because Sage Math, the first priority is to deal with the numbers as it is in real precision, rather than using it some approximation. So if you have to approximate it, then you have to tell that actually you have to look at the approximation number. That's what I'm saying. Yeah. Okay, fine. So let's generate something else. For example, let's. I also wanted to verify something else as well, right? For example, let's say what was let's create W1 is equal to V dot. What did you say? Span, right? Span, and then in the spans, let's throw V1 and V2. So now W1, if you print, then that should tell me two elements in the basis. And if you notice very carefully, the second one, 0, 1, 1, minus 2, is it the same? No. You see that the second vector is not 0, 1, minus 1, 2. And still, what it does is actually it gives me a sum basis. So what it's doing here is, it generates the vector space, who is the span of V1 and V2, and it retains, as far as possible, the best basis possible. Yeah. Okay. So here you can see actually it's an orthogonal basis. So that's the idea. So you have a best basis possible. Yeah. Now suppose if you wanted these two elements, of course V1 and V2, I know that V1 and V2 are independent of each other. So if I generate a subspace, then I can also have these two as a basis. That's also possible. The way I generate that, or the way I get that is, I can copy this entire thing, paste it here. So instead of span, I can have subspace like this. But now, meaning that gives the same result, whatever I have done it in this with a span. But now we also have subspace with basis. And now if you see, look at the basis now, they are the elements whichever we have supplied in V1 and V2. Yeah. So what did we achieve right now? So we just, now the basis is actually whatever the vector that we have given. That's the only thing happened over here. Well, why do I need all of them? Because sometimes you need to look at the corresponding coordinate vector, right? So what is a coordinate vector? Let's say, for example, if you have 1, 2, 3, and I can write this 1, 2, 3 as 1 into 1, 0, 0 plus 2 into 0, 1, 0 plus 3 into 0, 0, 1, correct? Now you can write this with any basis you want, like this. Now I have written it with using a basis, standard basis. Now, if you look at these numbers over here and then form them as a vector using that, and this becomes a coordinate vector. Okay. So typically, if you have a x1, x2, and so on up to xn, then you have, let's say, a basis v1 and so on up to vn. The first thing is, with respect to a basis, any element in your vector space can be uniquely represented by a linear combination. Yeah, meaning the linear combination that you write with respect to that basis is unique. That means you will have some a1 v1 plus and so on plus an vn, and this a1 a2 and so on up to an is unique, and that numbers we are calling them as a coordinate vector. So this is the coordinate vector of x1 and so on up to xn. Then more specifically, if you want to write with respect to the basis b, okay, do I call it as b? Yes, call it. So that's the coordinate vector. So you have any basis in your hand, you try writing a vector with respect to that basis or as a linear combination of the elements of that basis, and whatever the linear combination appearing over here, that we call it as a coordinate vector. Yes. So now, can we actually identify the coordinate vector with respect to whatever the basis that we are giving it? That was the question. Okay. So let's do that. What was our W? Our W was generated by this, right? So generated with this. And maybe for a simpler perspective, okay, let it be, not a problem. And let's define W is equal to a vector from QQ 1, 4, 7, -5. Okay. Now let me check what is my coordinate vector of W with respect to W1's basis. Now W1 dot coordinates of W, and that says vector is not in the free module, right? That means obviously this vector first of all should be in W, then only I can actually get the coordinate vector of it. So let's look at what is my W1. The W1 is actually generated from V1 and V2. And V1 and V2 are 1, 1, 2, -1, and 2, 3, 5, -4. Okay. So they are not going to be. So what will I do now? I'll change the vector a bit. So I'll put 0 here. I think that should work fine. I have the number here, should work. If I change this vectors, maybe I'll do one thing. I'll just take this vectors and then put it close to where I am. I redo everything. What did I do? I did created W1 using this two vectors, right? So V dot subspace with basis, and where the vectors are V1 and V2. Now that gives me the coordinates. So what did I do? I just made one small change. What is the small changes? Whatever vector I had in V2 was actually not having the vector W, which I wanted to check. So I changed the vector. That's all I did. Hopefully the change is easier to understand. So V1 is a vector, V2 is a vector, and we generate a subspace with those elements. Now we get a coordinate vector with respect to that basis. The basis is v1 and v2. Okay, let's probably verify that. We now use my v1. V1 is this. But what will I do now? I will also generate my v is equal to QQ4, and this also QQ, this also QQ, so that I don't have to see all this decimal places. So I'm being very careful now. I will not use any irrational numbers, so and so. We have already proved in the morning that you take any field, then k power n is always going to be vector space. So this has to work theoretically, and yes, it is working. So v1 is 1, 1, 2, -1, and v2 is 0, 3, 5, -1. So I know that if I sum them up, and I should get it. That's what this says. Because what does this means? This means that you take the 1 and then multiply v1. You take the 1 and multiply v2, and that should give me the vector w. Remember, this is the vector w, right? 1, 4, 7, -5. Okay. So if I don't do that, if I just simply do a subspace, what will happen? So what will I do now? I'll copy all of them now, and then I'm going to paste it down. So one small change is if I don't do with basis and then just subspace. Now you see that coordinate has changed. So you remember the initial way we had a coordinate 1 and 1. Now the coordinate is 1 and 4. Why is that change? Because now if you look at the W1, and it has a basis matrix different than V1 and V2. Because it's already orthogonalized it. That's what happened over here. So now all that I have to do is I have to verify it using this. So for example, 1 into, now I have a vector over QQ, 1, 0. I'm just trying the basis vector, right? So 1, 0, then 1 by 3, 1 by 3. You see, now it's a real calculation. It's not a numerical approximation, correct? So then plus 4 times the vector, and that vector is 0, 1, 5 over 3, -4 over 3. Yeah. So let's verify whether this is working fine. And that gives me W back. So the coordinate vector changes with respect to each basis. That's obvious. But up to the basis, it is unique. And that's why all this works. Simple. You see, if you take a two vectors distinctly, then that has to definitely form a basis. So either you keep that as a basis, or you can orthogonalize that and look at the corresponding orthonormal basis and keep that as a basis. So if you say with basis, then whatever the vector that you are supplying will become a basis for that vector space. If you do not say, then it will take the best basis possible. The best basis possible is usually the orthogonal basis. So it takes the orthogonal basis. Yes. Okay. Okay. Everybody good with that? So one portion I think we probably left is we did not check linear dependence and independence of vectors, right? Now remember, we do have v1, v2, etc. So we'll check there itself. Now we know who is my v. V is actually a vector space of dimension 4 over rational field. So now what we can do now is we check whether a particular set is a linear dependent set or not by supplying the vectors. For example, first of all, obviously, if I just give me one vector, is it linearly dependent? Single vector is not linearly dependent, correct? A non-zero vector is linearly dependent. Let's see whether 0 is giving me linearly dependent. If I put 0, then obviously it's linearly dependent. Yeah. And if I put two vectors, they are also not linearly dependent. Now, the way that linear dependence function works is, it will give you the coordinate vector, whatever I just actually found out. If they are linear dependence, then I know that there is some linear combination which will give me a non-zero coordinate vector, right? Meaning non-zero, I should not call it as a coordinate vector actually. So a non-zero linear combination is there. That means at least one of the coefficient is going to be non-zero. That's what it says. So it's going to give me 1. So for example, if I put 2 times v1, then I know what's supposed to be, right? v1 and 2 times 1 is linearly dependent. Agreed, no, everybody? Yeah. So the coordinate vector right now is 1 and minus 1 by 2. That means if you put 1 time v1 plus minus half times twice of v1, what will you get? You'll get 0. So the linear combination becomes 0. So that's what these numbers means. So these numbers 1 and minus 1 gives you the corresponding linear combinations. That's all. Okay. You know, once this works, then every other multiple also works. So I should not call it as unique, obviously. Okay. So you can take anything you want, like for example, v1 and v2. Clearly, it is independent because we just now noticed we had actually created a vector space with that. Let's say we add v1 and v2 and then put them together. So now it become dependent because v1, v2, the third vector is just sum of them. Therefore, what's the corresponding linear combination? So the best possible option is 1 plus 1 times v1 plus 1 times v2 plus minus 1 times v1 and v2. So that therefore the v1, v2, all of them gets cancelled and gives me 0 back. Okay. Yeah, if there is independent, the set is going to be empty. That's all. So maybe if you want to check independence, then you just have to check whether this length of that set is empty or not. Okay. For example, let me define a function to do so. I think now I'm getting into a little bit Python. So is independent. So that's what I want to check. So how do I check it? Now let's take an array of vectors. Let me call it as A. And then I have to return true or false. That's all, no? Yeah, either return or true or false. So when do I return true? If there is somebody, if there is nobody in the set, then I return true. Otherwise, I don't return true, right? Otherwise, I return false, technically. So when do I do that? So you also probably have to give the, let me take the vector space as well, from where I am actually trying to check the dependency as the input, okay? So what will I do now? So you take the V and then check the linear independence, linear dependence on of A. And this is going to return an array for me. So what I can do now is I can check the length of that array. If this is equal to, so if this length is equal to 0, that means what? That means this is linearly independent, correct? So we'll return true. if this if block is not passed through, that means actually we are actually dealing with the dependent set, so we'll return false. Simple as that is. Okay, fine. So we defined a function which will give me a independent true or not. Just a small helper function. That means now what we can do, we can use this function now. So is independent, where I have to supply my vectors. Remember, I can call v1 and v2 like this. Remember, these two are actually an array of vectors now, and that is okay now. And v is the v that we have actually just now picked up, or probably you right away pass through so that it is easier for us. That returns true for sure, because we know that we just looked at, right? The first vector was having 1 in the first coordinate, and then the second vector has 0 in the first coordinate. So obviously they are independent. So now all that I am trying to do, probably now we'll verify whether v1 plus v2. Now, what is the expectation? The expectation is that this should return false. Yes. Yeah. And it is returning false. So the way we check that linear independence is that way. At least I find it this is only best possible option. Yeah. Let's do one more small stuff. We'll take a W1. What was our W1 already? Okay, good. So it's generated by V1 and V2, right? What was our V3? V3 was 3, 4, 7, so on so. We'll put, we'll take W2. W2 is equal to V dot subspace of V3. So now what did I do? I actually have generated one subspace using V3, and that gave me this number. Now I have in my hand two subspaces, W1 and W2. Both of them are subspaces of V. Here it is Q power 4, correct? Q4. Now what and all I can do now? Clearly I can verify whether W1 is actually equal to, meaning whether W1 is equal to W2 or not. That means these two spaces are same or not, okay? So clearly that's false. That's because obviously the one of them is actually a two-dimensional vector space. The other one is single-dimensional vector space. So it's not element-wise checking. It is actually checking whether the subspaces are really equal or not. Okay. So in that way, what we can do, maybe what I can do is I'll try generating a vector space, which is it's too fast now. Yes. What did I say? Meaning, like, what do you want me to repeat? Like, which one? Definition of this one, right? Now, here what we wanted was we wanted to really check whether it is linearly independent or not. That was the question asked. So I use the linear dependence definition to define another function which will give me true or false based on the length of the coordinate vector, length of the linear combination vector which is giving me back. So if that length is actually equal to 0, that means that the given vectors are linearly independent. So I return true. If the diff block is actually not been getting in through, that means if the diff block is not active, that means it comes out meaning that that's actually not linearly independent. Therefore, I wanted to return false. So that's what this return says. If you are getting confused with this return, then what you can do is you can probably write else and then return false. Yeah, I have to learn typing now. Okay, it's clear now. Yeah. Okay. So I use that function in the next cell to check whether it is linearly independent in Q4 or not. Yeah, that's it. You can use any field you want. That's the beauty of Sage Math. Meaning you can define a vector in Galois field of order 2 or order 7 or whatever the prime number, and verify whether that is linearly independent with respect to that field or not. Is that okay? Okay, so what I was trying to do now is, I was trying to generate one subspace here. So W1 is a subspace generated by V1 and V2. Maybe I'll do it one more time here. So V dot subspace, and this time it is V1 comma V2, and so the W1 is having this basis, and W2 is having a single basis like that, meaning a basis with one number, one element. Now what I want to check whether W1 is equal to W2 or not. Obviously false, because one of them is just only one dimension. What I also can check here is, I'll check the equality first, but anyway, I'll check the equality next first. Let me check whether W2 is a subspace of W1 or not. Okay. What is your expectation? Supposed to be true or not? Yeah, actually dot is subspace actually will generate a subspace. What I wanted was is subspace. So W2 is a subspace of W1 or not? That was the question. Now I just asked the question to the Sage Math like this. That returns true. Why is it returns true? Theoretically it is correct. Why? Because V1 plus V2 is obviously part of W1, right? Because V1, V2 is two different vectors, and the V1 plus V2 is just a linear combination of them. Yeah. So the other way around is obviously false. Which one? Whether W1 is a subspace of W2 or not. That is false. Okay. Yeah. Print. Just print both of them. So you want to show both of them true or false, means like you have to print like this. Multiple lines also will work. You can print the first and then next. I'm little bit lazy, so I do it with two cells like that. Is that clear now? Let me zoom out a bit so that things are not gigantic. Okay. So now that we have a coordinate vector, so now what we can do is we can try writing something called as a change of basis matrix. I already raised this question in the previous session that can, if you have a vector which is written in terms of one basis, and I want to write the same vector into another basis with respect to another basis, can I do it and how to do it? Yeah. And that's easy to actually, first of all, theoretically develop. Let's say we have two bases. Okay. We'll call it as B and B prime. So let's say we have E1 and so on up to En. For a moment, I'll consider this is ordered. It's really not need to be ordered as long as you just stick to some way of writing it. That's it. The moment you write it, you should not change it later. That's it. Like if you write E1, E2, E3, then it's always should be E1, E2, E3 until you complete it. Don't write E2, E1, E3. So that's where we mean by order. So I always assume ordered in this fashion. So B, let's say we call it as E1, E2, E3, and so on up to En. And let's say we have another basis, E1 prime, E2 prime, and so on up to En prime. So we have two bases for a vector space V itself. Okay. So two of them are simply the basis of what I know is I know that if you take any Ej prime, it is first of all a vector of V. And I know there is a basis E1, E2, E3, and so on up to En. So what I can do now, I can find one AI, which will actually give me, I can find one A, the vector A or the set of linear, set of scalars. Let's call it as A1J E1 plus A2J E2 plus and so on plus ANJ En. Am I right? Is it clear for now? Because any vector can be written as a linear combination of the elements of the basis. Now I consider only this as a basis, and I consider all of these people are simply random elements in the vector space. So every element over here will be written as a basis, will be written as a linear combination like that. I know who is this AI, who is this AIJs? Who are they? They are the coordinate vector, right? For EJs, correct? So now what we can do is we can construct a matrix A for each E1 like that, right? So you look at E1, then what will happen? For E1, you will have one scalars. So A11, A21, and so on up to AN1, right? And for E2, I'm sorry, for E1 prime, you will have a scalars. And for E2 prime, you will have another scalars like A21, A22, and so on up to A2N, AN2, right? So finally, AEN prime no, the way I have written is just A11, A21 only, no? No, but the way I have taken is I believe this is supposed to be 2, correct? 1, 2, yes. Yeah, sorry for that. Okay. So that's supposed to be 1, 2. Maybe it is easy for me to erase and write. Okay. Yes. So similarly, here for final element, like what will I have? I will have A 1n, A 2n, and so on up to AN. Okay. So that's it. Yeah, you can change it. No problem. Hmm? J1, J2, since there we wrote A1, J, A2, J, here we have Correct. Those coordinates are coming no, what you really wanted to see is the A transpose. A transpose will give you the nice look. But technically, these are the coordinates, no? We cannot change it. So the way actually it has been generated, we cannot change this, although it looks little bit not really normal to us. Yeah. Sometimes I also get confused with them. So I always keep notes with me. I wanted to be very careful. See, no need to actually really bother about this portion over here, whatever I have mentioned. You just have to bother only about this portion. Is this clear or not? That's all I wanted. That's clear. So for every such EIs, for EJs, EJ primes, we have such coordinate vectors, and you throw them into the row of the A. That's all. Yeah. Now, what is actually technically we have done here is, if we take a vector V, then I know who is this fellow. This fellow is with respect to a basis E1, with respect to the basis B prime, we will have some A1 prime E1 prime plus and so on up to AN prime EN prime, right? Yes. So that means now we will have some A1 prime and so on AN prime times E1 prime, E2 prime, and so on up to En prime, right? Writing it in a matrix format now. That means now what is it now? So this is actually equal to row vector. I'm writing it as a row vector. This is a row vector for me now, okay? So now I know how to write these row vectors in my hand. So those row vectors are whatever is there in my AN prime, and these row vectors can be written as, remember initially I had written column, now I can convert into a row vector like this, A transpose times the row vector E1, row vector E2, and so on up to row vector En, correct? So hopefully that's clear for you. Yeah. Still more? See, what is technically happening over here is just put the columns whatever you want. This is what you like to see in the middle, A transpose, and that is happening here. Yeah, fine. Yeah. I call it as A transpose, that's all. That's, I think mostly because it's technically started with column vector and therefore like that, but I think I started with row vector. I'll change it next time. Yeah. Yeah, fine. So what do we do now? I know that there is only unique representation with respect to a basis. Therefore, if you are writing V with respect to E1 prime, En prime like that, then what should happen? I know there is a unique representation of V with respect to E1, E2, and so on up to En. And if that happens, then what does that mean? If the vector V is been written with A1, E1 plus and so on up to plus AN, En, then it is clearly, I'll say if this happens, it's clearly saying that A1 and so on up to AN must be equal to this fellow, correct? Because that fellow is the linear combination using E1, E2, and so on up to En. There cannot be two different coordinate vectors. The coordinate vectors are unique. So therefore, this fellow must be A1 prime and so on up to AN prime times A transpose. That's it. So what did we prove actually? What did we prove is, if I have now, what's the representation says? It says if I use my A transpose, then I have a different way of writing the given vector. It's just the way it's changing. I'm writing the same vector, but the way that I represent it is entirely different. That's what it says. Okay. Now you can prove that this A is actually invertible clearly. And that's pretty easy to prove it. Even if you are not right now proving it, if you look at the corresponding linear transformation stuff later, and that is easy to prove as well. Because all those people are simply a coordinate vectors. They are all unique in nature. And all the vectors that we wrote it is entirely elements of basis. So obviously it must be invertible. Which one? We can do that. Why? Because that's because you take one more basis, no, then we will have the coordinate vector problem, no. We'll have to find the coordinate vectors correspondingly and then do it. It will take time. That's why I do it. Yes. Oh, we'll do it while we're doing it in Sage Math. Easier to do it there. Are you sure? You take one basis, one, comma, one, I mean, one minus one, comma, one. Another one, comma, minus one. Okay, let's do that. 1, comma. Okay. 1, comma, minus 1. So with respect to 1, 0 and 0, 1, I know. Huh? Okay. You have one more? Any easier one? Probably we'll take that only. Yes. Yes, that's all. I was about to write like this. Yeah. Then what are we trying now? So we'll try writing the each basis, meaning each vector 1, comma 1 into a basis of 1, 0, 1. So that is, I think that's clear, I guess. 1 into 1, comma 0 plus 1 into 0, comma. So this 1 and 1 I'm saying. So now this 1, comma 1 and similarly 1, comma minus 1, right? So 1, comma minus 1 is actually equal to 1, comma 1 into 1, comma 0 plus minus 1 into 0, comma 1. That's all. So what's my A? A is 1, 1, 1, minus 1. That's all my A is. Okay, this is this. Huh? Okay, we change the second vector to minus 1, sorry. We change second vector to minus 1. I think it's better we do it in some tutorial session or something. Okay, one question. Is this change of basis from B to B prime or different? What do we try actually? We try B prime to B, right? We give up base, I mean, where we want to go is B. Okay. Is all convinced now, everybody? Or confused? It'll get clear actually when you are doing it in Sage Math, actually, pretty easy to do it. Usually it is like that. Okay, so we'll assume that everything is sorted out right now and we'll go forward. So what we have actually done here is we have found a base, we have found a change of basis. No, I think I said wrongly. We found a base change of basis from B to B prime only. But what I said was actually B prime to B. Yeah. Sorry. Yeah. Okay, I'll write the theorem so that you will be happy, I guess. Suppose if you have A1 and so on up to AN as the coordinate vector of coordinates of a vector V in B with respect to the basis B. Okay. Now what we wanted the basis, we wanted the coordinates of V with respect to B prime. Okay. So then the coordinates of V with respect to B prime can be obtained by computing A1 and so on up to AN times A transpose inverse. That's it. Okay. Now probably I'll call this fellow as my A1 prime and so on up to AN prime. Meaning I'm generating a new vector using this. So in this case, I will call this A. I'll call this A as a transition matrix. So I'm not calling the A transpose as transition matrix. So I think now it's clear. Yeah. So we'll do it in SageMath so that we'll get some idea. Good. So in other words, what you can do is, as some of you have already suggested, you look at the corresponding coordinate matrix, coordinate vectors over there, and then put them in the column and do a transpose. That will also do the same thing. So all of them are okay. Yeah. In fact, for now, actually, we are going to do that one. Let's take, let's do a change of basis now. Let's keep simple V is equal to R3. Let's take U is equal to a vector in R with 1, 0, 0. There's actually one more way of getting this vector, you know. This one is actually what? This is actually 1, 0, 0, right? Now, you know, V is R3. So if I write the generator of V, the first generator of V, if I give it, then that gives me the standard basis vectors to me. v dot gen of 0 will give you the first vector in the standard basis. Then if you do a second vector, then it is 0, 1, 2. That means it's a third vector. The third vector is 0, 0, 1. Okay. So instead of me doing all this u1, u2, u3 stuff, writing it, either you do it this way or you manually you can do v dot gen of 0. That's what I'm trying to say. Okay. Fine. So similarly, you can do u2. u2 is vector 0, 1, 0, and u3 is a vector 0, 0, 1. Okay. Fine. And what we will do is we'll construct a basis. The basis is simply the vectors consisting of u1, u2, and u3. That's clear. And similarly, what we will do is we'll have three different, one more different basis. We'll construct 1, 1, 0. And v2 is equal to vector 0, 1, 1, 1. v3 is a vector 1, 0, 1. The basis b2 is equal to, it's an array of v1, v2, v3. Okay. So now what we'll do is actually, let's assume that the vector spaces, meaning the subspace, is actually written with respect to the base b2. Okay. Now what we wanted was the coordinate matrix A. Probably you please keep compiling it, otherwise sometimes when you make some small spelling mistakes or whatever it is, you will find it problematic. Okay, I'll zoom out a bit so that I'll fit everything. Maybe I'll remove some spaces. So the A is equal to, what we can do now is we'll find the coordinate vector and then we'll transpose it. I think that's better option now. We know how to find the coordinate vector now, right? So you see, I want the coordinate vector with respect to this B2 basis. That is the stuff. So the way actually you do that is w dot coordinate coordinates. And what do you want? I wanted for every u1, u2, u3, correct? So let's write u1, and that gives me the vector lengths. Yeah. Now I wanted it for all the elements. So the way I do usually is I'll use a now I'm going to little bit Python. So I can surround it by a bracket like this. So it's called as list comprehension. So you take only the coordinates of u for all u in the B1. So now that will give me all the vectors of B1 now. Is that okay? So I found all the coordinate vectors. Now I know if I do a transpose, then that's what I need. First of all, I have to make this as a matrix. Now, if we surround it by a matrix function like that, it's a method available there. in Python, sorry, in Sage Math. And there, that now it will become a matrix. So now what we can do, we can actually write it as a, if you want a transpose, then you can do a transpose like that. Now it has given me a transpose. So all that I'm going to do is just cut this, all of them, and put it here. Okay. Fine. So this A is the change of basis matrix. I think I can do a show of A that will give me a nice LaTeX representation. What I did is, huh? Okay. I'll show you. Got it. For typing, how to type faster, how to type everybody knows. Typing has now become a must. Yeah. Which I'm bad at. If I have to type something more in WhatsApp or Telegram, come to web.whatsapp.com, type faster. Uh-huh. Ah. So I should find a way to feed it into the brain. No? So that's why that's the way actually that's why I use this little fellow to actually feed it into your brain. It's okay. So I'll do one thing. I'll leave you here with some more works so that you can do remaining half an hour. At least you can practice what we have done with this following questions. Now, what you can do is change this basis first. First of all, these are the questions. You can try doing it. The first question is, what if the field of reference is changing or field is changing? Actually, in a way, what I'm saying is, what if the vector space itself is changed? How is that computation? And then do the same thing for whatever we have done now. So the same thing makes some sense now, ideally, for polynomial spaces as well. Maybe take a polynomial of degree less than or equal to 3 or 4, whatever it is, and do that. Yeah, that's what I'm telling you to figure it out. Just go to a Sage Math manual and you figure it out. It is pretty easy to do it. It's just you have to change one line over there. Yeah. So at least for the polynomial space. And also you can do the same thing for any matrix spaces as well. So these things you can try. I had some more things to cover in linear transformations, I believe. What we do? Ah. Otherwise, I'll adjust it to the tomorrow session, linear transformation. So I'll start with linear transformation tomorrow, and then I'll go to slowly matrices, decompositions, etc. This is just if you look at the cell over here, right? If you go above, you can change it. I used a shortcut here. If you change it to markdown, then it is. The rest of the half an hour is, I think we'll leave it for tutorial so that we'll have some practice on it. Tomorrow we'll do linear transformation and decompositions. Yeah. Today evening, anyway, we will do some graphs as well. So tomorrow we'll try to use that as well together. So it will become now better. Whatever I have done, I'll share it in the group. I'll share a better version in the group with some writings over there. Ah. Okay then. So can you turn off the live YouTube live? I think YouTube live is not required now.